Binomial heap running time. The running time of most operations in a binomial heap depends on the number of trees. Property number 3 gives us the following theorem. An n-node binomial heap consists of O log n binomial trees. Here are the possible binomial trees and their number of nodes. Let's take for example this heap. This is the only possible configuration for n is equal to 7 nodes. And as you can see, it has all the possible trees. Compare that to n is equal to 8, which has only one tree. The left heap shows the worst case scenario for a binomial heap. Since the sizes are different, the worst case for an n-node binomial heap is to have one type of each binomial tree. That is, the binomial heap is composed of b sub 0, b sub 1, b sub 2 up to b sub k binomial trees, totaling n nodes. This means that the summation of 2 raised to I, where I goes from 0 to k, is equal to n. Let's simplify. The summation will just be equal to 2 raised to k plus 1 minus 1, since it's a geometric series. And let's get k. So k will be equal to log of n plus 1 minus 1, which means that the number of trees in the maximum is O of log n. Binomial heap operations. First one is find min. To do that, we do a linear search on the roots, since each root is the minimum for that tree. Best case is when there's only one tree, or when n is equal to 2 raised to k, that's O of 1. Worst case is when n is equal to 2 raised to k minus 1. This is the case that produces the maximum amount of trees, which is O of log n. Merging. Remember that there can only be one type of tree in a heap. Therefore, we combine same-size trees into one. Take note that we should preserve the min heap property. Therefore, the bigger root should be the child of the smaller root. Let's have another example. How do we merge these two heaps? This is like merge from merge sort, only it's not allowed to have two trees with the same size. So let's do that. Here's the same trees, same heaps rather. So let's compare the first trees. So one is smaller, that's the tree containing 7. So we put that first in our new heap, like so. Next we compare these two, but they're of the same size. So we combine them, then put them in, like so. We're left with only one tree, but it's the same size as the previous one, or the current one in pointer tree. So we also combine them, like so. And that's O of log n, since we went through each tree once. Now what if we want to insert a value? We treat that as a special case of merging. It's as if we're merging our heap with a singleton tree. And that ends our discussion on binomial trees and binomial heaps, and in trees in general.